When you're dealing with equilibrium calculations, one common little tool that's used to try to make things as painless as possible is a little technique that's commonly called the ICE method. So, for example, let's take the following system at equilibrium. And let's say the equilibrium constant is 143. All right, let's find the equilibrium concentrations of all three when you start with 0.5 molar H2 and Br2. So one thing to help you figure out a problem like this is to set up a little table that's commonly referred to as an ICE table. And ICE, ICE, stands for your initial concentrations, C is your change in concentrations, and E is your equilibrium concentrations. So we're starting with 0.5 molar of each reactant. And they didn't mention anything about HBr, so we have no product initially. So for this thing to achieve equilibrium, first you have to make some of your product. So you're going to lose X amount of each reactant, and given the stoichiometry, when you lose X amount of bromine or hydrogen, you gain 2X worth of product. So at equilibrium, you have 0.5 minus X of each reactant, your initial minus the amount you're losing during as it shifts to the right, and you're going to have 2X worth of HBr since you didn't have any to begin with. So we know the equilibrium constant with respect to concentration is going to equal the concentration of our product squared, because it's a coefficient of 2, over the concentration of each reactant. We're given a value for K, and given that last row in our ICE table, we know a little bit about the concentrations. We know the concentration of our product is equal to 2X. So we'll plug that into our expression for K. And each reactant is going to have an equilibrium concentration that's equal to 0.5 minus X. So what you have to do now is you have to solve for X. And how you solve for X is going to vary from problem to problem. All right, for this particular problem here, probably the best way to do it is the two terms at the bottom are the same, so we can say 0.5 minus X squared. And if we take the square root of both sides, square root of 143 is 11.96. You take the square root of the right side of this equation and it removes the squares. So the square root of 2x squared is just 2x. And 0.5 minus x. So you continue to solve for x, and eventually you'll get x equal to 0.43. So the concentration of our product is equal to 2x. So 2 times that will be 0.86. Concentration of each reactant, they're both equal to 0.5 minus x, which gives you 0.07. There's a pretty simple way to check your work. If these are actually the concentrations of these three parts of our equation, then when you plug those into this expression for K, you plug 0.86 into the top part, 0.5 into each one of your reactants, plug those in, you should get an answer that's reasonably close to 143. If it's not, and usually if it's not reasonably close and it's way off, then you probably did something wrong and you need to go back and check your work.